If you have a data terminal like this Bunkeramo right here, and you want to turn it into an admittedly terrible typewriter, all you have to do is jumper pins 2 and 3 of the DB25 connector on the back, and everything you type will loop straight back into it and be printed on the screen. Super easy to make a terrible typewriter. Or you could do what I did and build a homebrew computer from scratch based on the TMS 9900 16-bit CPU out of a TI-99 home computer, throw some ROMs, RAM, and build a UART circuit on a breadboard so that every time you press a key up on the data terminal, it sends 8 bits of ASCII data into the computer, which then receives it and echoes it back out up to the terminal. Cut. I quit. All right, let's try that again. See if I can do this without corpsing the scene here. If you're not familiar with what's going on here, here's a quick 60-second rundown. Sitting on top is a Texas Instruments Insight Series 10 data terminal. It's about as dumb terminals can get, but I think it's adorable. It's absolutely gorgeous. And it's hooked up to my homebrew computer that we've been building from scratch. This thing is based around the TMS 9900 CPU that is famously out of the TI-99 and 4A home computer. But more importantly, that CPU is derived from the TI-990 mini computer CPU. That means it has a 16-bit data bus and a 15-bit address bus. This thing can support 64 kilobytes of memory space, but it can only address those one word at a time. So it can only handle 32 kilowords, and to count to 32 kilowords, you only need 15 bits. Now, I'm not using anywhere near all of that memory space. I only have 2 kilowords of ROM and 6 kilowords of RAM. Now, I am doing something a little off-brand here because the TMS 9900 has something called the CRU on it, which is the Communications Register Unit or something like that. I don't know. It was this hyper confusing 1-bit thing that you kind of half address. I didn't want to deal with it. I kind of wanted to do things a little bit like Centurion does it. So everything that is in the input-output space or the I/O space is being handled through MMIO, or memory mapped input-output. So whenever I push a key on here, this data terminal sends out an 8-bit ASCII value into my breadboard monstrosity here. There is a chip on here called a UART that receives that and takes it in as serial, creates it as parallel, and sets off a flag. That flag is tripping an interrupt request within the CPU and setting an interrupt level. The CPU sees that, jumps to a specific location, services that interrupt request, and the current code that's on there just takes whatever was in the UART and stuffs it right back into the UART and tells it to send it back out, creating the world's worst and most complex typewriter on the planet, and it was a phenomenal amount of effort to get it there. So, how did we get it there? Well, let's take a look at the hardware in a little more detail. And this is the schematic right here that we're using for the UART on the breadboard. Whenever I want to transmit a character out up to the data terminal, I need to first check that the transmit holding register is empty. The UART has a specific pin for that, THRE, so I'm gating that with a NAND gate that goes into another NAND gate to create an AND gate. The signal that I'm gating that with is THRE1 here. That is an MMIO signals, and that memory address is going to be F000. And I'm using a ROM chip to do all of this decoding. And so that MMIO address gates the THRE signal, which then makes its way over to a little transistor that is sitting on the data bus. And essentially, whenever the transmit holding register is empty and we hit the correct MMIO address, that transistor is going to turn on and it's going to pull that specific pin of the data bus low and hold it there. What that means is that I can then read the data bus and check that specific pin, and if it's low, then I know that the transmit holding register is empty. So I can now load a new value into the transmit holding register, and we do that with THRL, transmit holding register load. And you can see there's a specific pin for that, and we just have another MMIO address pin going straight to it. Whenever that happens, the UART copies whatever's on the data bus into itself and starts transmitting it out on the transmit out pin, which is pin 25 up here. Now that transmitted data out is going through an OR gate to buffer it up, and that's going into a PNP transistor that's going between +5 volts and -12 volts, but there's a 10K ohm on there, so we get about a +5 to -5 swing, which is just enough for RS-232 serial, and this can detect that. Now, whenever I press a key on the data terminal here, it's going to send 8 bits of ASCII data serially back into the UART here. So we need to be able to capture that and present it to the CPU in some way, but we already are running into a pretty big problem in that this thing is RS-232 levels. So I need to level shift that so that I don't blow up my UART. So when it comes in, we're going into this interesting transistor and diode combination here. The diode is clamping everything to ground. So whenever we're at negative voltage, the diode prevents that going negative on the base of the transistor. And then the transistor is just a +5 volts. This level shifted output is going through an OR gate into the receiver input on pin 20. And whenever a full byte is received, the UART kicks off the data ready flag, which is on pin 19, to let the computer know that it's received a byte and it's ready for the CPU to come retrieve it. If we look at the data ready pin, I've got it going into 4 transistors, like individual transistors. So how are we using this to tell the CPU that a byte is ready to receive? Well, one of these transistors is going to an interrupt request line. The CPU sees this transition down to 0 volts and says, oh, hey, an interrupt has come in, and it's going to try and interrupt the CPU from doing whatever it's doing and tell the CPU to go off and handle this thing that's happening. But multiple interrupts can be coming in from multiple different devices, and some devices are more important than other devices. So there's 4 bits dedicated to setting an interrupt level. I'm only dealing with 3 here because it was easier that way. I was trying to make things compact and I figured I wasn't going to use all 16 interrupts. But essentially these 4 bits set a binary value, and the CPU will look at that binary value and make a decision. If the binary value is lower than the current interrupt that the CPU is servicing, then it'll handle this new interrupt that's come in. So I'm not setting the highest, most significant bit. So all of my interrupts start at level 8 and we work our way up from there to 15. So I want this to be a level 8 interrupt. And since I'm not doing anything with that most significant bit, I need to pull all 3 of the remaining bits low. So I get a binary value of 1, 0, 0, 0. The CPU will see this new interrupt level and say, hey, I'm ready to service that. So it'll jump to a specific set of code where it will then hit the receiver register disconnect pin, connecting the 8 outputs onto the data bus, and then it'll pull that byte off of the data bus. And finally, the CPU will hit the DRR pin, or data ready reset pin. And essentially this resets the pin 19 data ready to essentially say that it's done. We finished. The UART is ready to receive the next byte. So there we go. That's the hardware. It's actually pretty simple, even though it took me a long time to get it set up. But this hardware is useless without software that is written in such a way that it can handle these interrupts. And so here's a program that I wrote specifically for doing that. The first instruction is RORG0000. This is the reset vector. Essentially what happens is whenever you power on the machine or hit the reset button, the CPU is going to jump to memory address 0000, and it's going to read in the workspace pointer and a new program counter that tells it where to jump to start executing code. Now, it's probably important to talk about the workspace here. The workspace is a collection of registers in memory. Like, that's it. The CPU doesn't really have any internal registers. I mean, it has a couple, but they're not really accessible to the programmer. All of the programmer's registers are located in random access memory. So I set the workspace pointer to be 1000. That is the beginning of random access memory, and there are going to be 16 16-bit registers available for me to use at that location in memory. But the next instruction is RORG0020. This is interrupt level 8. So whenever a level 8 interrupt is received by the CPU, it jumps to location 0020 in memory, and it reads in a new workspace pointer and a new program counter. That new workspace pointer is 1020. This means that we have a completely different set of 16 16-bit registers available for us to use. So we can switch contexts really fast, and we don't have to worry about clobbering registers for other parts of the program. That's really nice. Now let's do a couple of definitions here at the beginning of our program to make things a little easier. And once we've defined all that, let's get into the proper program loop here. Our first instruction is LIMI. This is just essentially telling me which interrupts I'm listening to. And then we get into our proper program loop here, which is just loop, jump, loop. That's it. Our primary program here is just jumping to itself on an infinite loop. So the program is running infinitely, doing this jump over and over and over again. But whenever I hit a key, the CPU sees that as an interrupt, and it interrupts our loop, jump, loop here, and it services that interrupt by jumping down to 0020, reading a new workspace pointer, and then jumping up to 0100, which is our next step of the program, which is our actual typewriter program. And we're gonna move at RRD, which is again F004, and we're gonna move that into R1. And then we're gonna do a move B R0 to et DRR. Now this is a bit of a weird instruction because I don't actually care what's in R0, and I don't actually care what it's putting on the data bus. All I care about is that we hit memory address DRR, which will reset the UART and get it ready to receive the next byte. Now, we have the UART properly reset, and we have the byte that we just received sitting in memory in register R1. And we're gonna do a move et THRE into R2. And then we can now test register R2 to see if the transmitter holding register is indeed truly empty. And we're gonna do that by doing an AND immediate of R2 against 0001. Now, if the least significant bit is 1, that means that we're going to get a value of 1 in R2, and we don't want that. We want a value of 0 in R2. So the next one is JNE send, or jump if not equal to 0, back up to send. If it is empty and we are ready to receive a new byte, we pass right on through JNE down to move byte R1 to memory address et THRL, which is going to tell it to grab the 8 bits on the data bus, pull it into its internal buffer, and start transmitting those out serially over to the data terminal. So that is my super simple program that we're using to test whether all the hardware is working correctly and whatnot. And it's not pretty, it's not elegant, but it got the job done. There is a much better way to write this program, and I've got that right here. And actually, I figured this out with the help of my buddy Urbite. I'm just going to use his online moniker. And if you want to Google who Urbite is in the context of TI-99, you might be able to figure out that I have one of the greatest buddies on the planet when it comes to Texas Instruments stuff. This is a much more elegant way to write it. And when we get this stuff cut out onto actual PCBs and installed into the chassis here, we're gonna run something much more similar to this that's much more elegant. But really what I wanted to do today was just prove that it works. And as you guys have seen already throughout the episode, everything I type gets echoed back absolutely perfectly. But what's more interesting is that if we look down at this DE9 breakout box, they have little LEDs for receive and transmit, and we can see that those illuminate in sequence. So we can actually see the byte coming into the computer and then getting echoed back out from the computer. But here's something that I haven't actually tried yet. Keysight donated this absolutely epic 4-channel scope, so let's put it to use. If we look back at the code here, we can see that when we get to our interrupt, we're gonna hit all 4 memory mapped IO addresses in rapid succession. So if we put the scope on all 4 of these, we should see all 4 of them toggling in perfect sequence every time I press a key. Okay, I think I have everything plugged in correctly, so if I start pressing buttons, I can see that it's flashing something, but we gotta do a single shot to see what's going on here, so... All right, that is very different than I was expecting. The yellow trace here should be transmit holding register empty, so I have no idea why we're pulling to see if the transmit holding register is empty so much. The green trace should be transmit holding register load. I have no idea why we're hitting that twice. That looks incredibly wrong to me. We should really only be loading a character in once since we're only echoing a single character back. But the two traces above that make a little more sense. The blue trace is receive register disconnect. And then DRR is the red trace here, which is the data ready reset. So we received it and then we reset, and then we should be sending it out like somewhere here, but I have no idea what's going on with our transmit stuff through here. Like this, I feel like that shouldn't be happening. All right, I'm glad that I actually did this because I took a minute to try and analyze what's going on. We should not be having transmitter holding register load and transmitter holding register empty toggling as much as they are. And the only reason that they could be toggling that much is that I've got the microcode in my little ROM here that's doing all the address decoding wrong. And I went back and looked at my notes, and I do definitely have it wrong. I've got it correct for F000 and F002, but I've got it completely incorrect for F004, F008, and on. And it needs to be 0F, 0C, 0A, 06, and then 0E on repeat. All right, I've got my laptop set up here with the ROM burner and the ROM pulled into it, and this is the microcode that I burned to it, and you can see, yeah, 0F, 0C, 09, 05, and then 0D on repeat. I need to change this to be 0F, 0C, 0A, then 06, 0E, and have 0E be on repeat for the rest of it. So that's gonna be a little tedious here. There we go, that should be, let me just double check, 0F, 0C, 0A, 06, 0E on repeat. But we'll go ahead and save that, and then we'll move over to the terminal here. Now, for everybody screaming at their screen, there's probably a way to have modified that binary file in the terminal. I don't know what it is. Octeta works just fine for me, so that's what I'm going to do. Okay, now we want to program that onto the Atmel chip down here. So we're going to run mini-pro, and we're going to use a -P. This is an AT28C64B, and I think that'll work. We want to do a -S, then a -W, and the file that we're going to write is ucode.bin. Let's go ahead and hit enter. And yeah, there we go. We just wrote the new code to it. So let's pop that out, put it over back into there and see how our scope changes. Hopefully it looks like it's supposed to now. All right, ROM chip is back in. Let's flip the power on here. Let's see if we broke it. Of course we did. Of course we did. Nothing is echoing back now. Okay, what did we change here? Oh, that looks dramatically different. All right. How come it's not echoing back? Oh, no. So the blue trace here is receive register disconnect. That goes active low so that the receive register is put on the bus. The purple trace here is data received reset or data ready reset. That goes low and resets are interrupt. Then the yellow trace here is transmit holding register empty. That pulses high to check if the transmit holding register is empty. It is indeed empty, so we do a low toggle on the final one here, which is transmit holding register load, which should load in the byte to shift out. This is what it's supposed to do. How come it's not working now? How come it worked when it was broken, but now it doesn't? All right, it's been like 4 hours since I last saw you guys, and I've started and stopped filming like 6 times, and all of that footage is just gonna get thrown away because it was wrong. And it's like late on Friday. It's gonna be a rough video edit tomorrow. Oh, I hope I can get it done before Sunday. So if you're watching this on Sunday morning, you know how it went better than I did, because I'm gonna be up late Saturday editing this thing. All right, so what was going on? We saw that we had transmitter holding register load and receiver register disconnect kicking off at the same time. This was a microcode fault. We fixed the microcode, which broke everything else. And what it didn't really break everything else. It highlighted a different fault. And that fault was that the byte was never making it to the CPU in the first place. Or more importantly, the byte was never making it out of the CPU back over to the UART. But how can that be? It seemed every time I typed, we actually did get text coming back out on the data terminal. Well, what was happening is that since we had transmitter holding register load and receiver register disconnect happening at the same time, the UART was basically feeding itself. It would put a value onto the data bus and simultaneously pull a value off of the data bus. So once we fixed the microcode, now the CPU is not putting the correct value into the UART, and the UART's not printing anything out, and we're broken. So what was the fault? Well, we had two faults, and I think we might be teetering on the edge of a third fault. Initially, I was thinking it was speed. It takes 500 nanoseconds for the UART to put a value on the data bus after receiving the receiver register disconnect signal. For reference, the RAM takes 200 nanoseconds. So I actually tried a faster UART. This is an Intersil IM6402. This is a much faster UART. It takes like 80 nanoseconds to get data onto the data bus, but it is pin compatible with the TR1602 that I'm using in there. And no difference. Didn't fix it. So that wasn't the problem, although I think that's something that we might need to think about in the future. The problem was actually that I had two wires for our MMIO decode backwards. So once I fixed those, that didn't change anything. The bigger issue was in software. It's always a software issue, isn't it? So in the code, when we're ready to send the byte back out to the UART, I'm doing a move byte R1 to etTHRL. But the problem is that I'm moving a byte. This is a word-based machine. So if I'm moving a byte, I'm only moving half of a word. And I don't really know which half, and I think I'm moving the wrong half. Because if I change this to just move a word, it works. We're back to typing, it's back to working exactly like it should. So that was it. That was all it was. It was a simple move byte that should be a move word. And I think what's happening is it's moving the upper byte and I want it to move the lower byte. So instead I just move the entire word and the UART just doesn't pay any attention to the upper byte. So crisis averted. In the next episode, what we're going to do is we're going to try and get all of this onto PCBs plugged into a backplane, so this is all nice and tidy. And we're also going to try and get some buffers on there because I'm starting to get a little worried about the CPU being able to drive all of the peripherals that we have. So that's what we're doing in the next episode. But for now, I'm going to go inside and start trying to get the edit done in time. So I want to thank you all so much for hanging out with me today, and I hope to see you in the next one.